What is in-vehicle networking, or IVN, about? Wikipedia says in-vehicle networking is a specialized internal communications network that interconnects components inside a vehicle. This communications network requires both software and hardware that are both following certain standards. The software is standardized by various initiatives. The latest one is AUTOSAR, which is currently being introduced into mass production. Before AUTOSAR, the software standards were pushed forward by the HIS Group. The HIS Group was founded by the German OEMs Audi, BMW, Daimler, Porsche, and Volkswagen. OSEC is a trademark of Continental. Both HIS and OSEC are still active. In this presentation, we will focus on the hardware aspects of in-vehicle networking. The main standards in use today are LIN, CAN, FlexRay, and MOST. Ethernet has also started to enter automotive applications for a limited set of applications. Next to these major standards, you can find other standards that are used for niche applications, e.g. LVDS or PSI-5. We'll neglect these for the time being and have a closer look at the major standards on the next slide. The major in-vehicle networking standards of today are LIN, CAN, FlexRay, Ethernet, and MOST. The transmission medium for LIN, CAN, FlexRay, and Ethernet are copper wires. Except for LIN, twisted pair wires are used as they have the characteristic to eliminate electromagnetic interference almost completely. The MOST bus is an exception to this, as it uses optical fibers as transmission medium. By design, optical fibers are not susceptible to electromagnetic interference, but they come at a higher price and less mechanical flexibility, i.e., they break if the bend radius is too small. The LIN bus operates at either 10 or 20 kilobit per second. It is supplied directly from the battery at typically 14 volts. This means no separate voltage supply is needed, which is the first cost saver. Second cost saver is that it doesn't use differential signaling, i.e., it requires a single bus wire only, and is therefore sometimes referred to as a single-wire bus system. Overall, the LIN bus is the system with the lowest system cost. The CAN bus also comes with two speed options: the FT or fault-tolerant CAN at up to 125 kilobit per second, and the HS or high-speed CAN at up to 1 megabit per second. The CAN bus introduces differential signaling on the twisted pair bus wires to avoid common mode interference. Another benefit of differential signaling is that it eliminates the so-called ground shift. Ground shift refers to the fact that the electrical potential between different components of a vehicle may change over lifetime, e.g. by means of corrosion. The CAN bus is currently the most widely used communication network in vehicles. The FlexRay bus system offers up to 10 megabit per second bandwidth. It was introduced into mass production by NXP in close cooperation with a major OEM already in 2007. Next to the increased bandwidth, one of the major benefits of FlexRay is its completely deterministic behavior. Only with FlexRay, a transmitter on the bus knows exactly by when its messages reach the receiver. This is not the case for the CAN bus, due to its relatively random arbitration mechanism. The determinism and speed of FlexRay makes the system particularly well suited for safety-critical applications. As of today, FlexRay is the fastest AEC Q100 qualified electrical automotive network on the road. Ethernet is already being used for vehicle diagnostics in the garage. Typically, the body controller or gateway of a car is connected via Ethernet to a PC running the vehicle manufacturer's diagnosis software. Recently, a discussion about using Ethernet for camera-based systems has been started. IVN is everywhere. Without it, a modern car would not run, as each electronic control unit in a car has at least one IVN connection to communicate with other control units in the car. Already back in 2007, approximately 2.6 billion IVN nodes were implemented in vehicles. The number of networking nodes in a car varies from 4 in cars for the fast-growing emerging markets to an average of approximately 30 nodes for the premium cars. Some luxury cars even feature more than 100 networking nodes. This simplified block diagram shows a typical network architecture of a modern car. There are up to 6 main network branches that are interconnected by the gateway or body control module in the car. Let's start in the upper mid and look at the network branches clockwise. The instrument CAN connects the dashboard and instrument cluster as it requires data from other parts of the car, e.g. the speed data from the powertrain bus. The MOST bus clusters the infotainment system, including radio and navigation systems. The CAN-C is one of the CAN buses in the body and chassis area interconnecting various control modules. To limit the physical load on this CAN bus, it is often supported by a second CAN bus, the CAN-B. It is the powertrain bus that links up all the electronic control modules required to make the car move. Due to its high bandwidth requirements, the powertrain bus often uses state-of-the-art FlexRay technology. The Clamp 15 and Clamp 30 color code is used for the various standardized power modes of the vehicle and will be explained later. Let's now look at some specialties of this in-vehicle network. The diagnosis bus may be either a CAN or Ethernet connection. The deployment of Ethernet for this bus is relatively simple, as this bus is never active when the car is on the road. It's purely for diagnostic purposes in the garage. Therefore, the requirements for electromagnetic compatibility are much lower, and Ethernet is a good option due to its high bandwidth. There is also direct communication across the network branches through direct connections without using the gateway or body control module. This is typically done for very time-critical and safety-critical tasks, where low latency is crucial. A good example for this setup is the electronic stability control, often referred to as ESP. In order to start countermeasures in case of a critical driving condition, the powertrain branch must closely monitor the state of the car. Important parameters are the steering angle and the level sensor data. Combining these parameters with the current speed of the car allows to determine if the car is too fast for the current curve radius. The car may then decide to lower the speed by braking to save the car from braking out. It is obvious that for such a safety-critical application, absolutely no latency that may be introduced by the gateway can be tolerated. Another specialty can often be seen on the MOST bus. That's the ring topology. The advantage of the ring topology is that communication on the bus may continue even if it is physically broken in one place. Also, there may be multiple active communication channels on different sections of the bus. The disadvantage of this topology is its complexity in terms of protocol overhead and physical connectors. In-vehicle networking follows the ISO OSI model. NXP's high-performance mixed-signal strategy focuses on the physical layer of the multiple ISO OSI layers, as this is where NXP's extensive experience is most important for outstanding network performance. The layers above the physical layer are handled by the microcontroller. NXP is the undisputed market leader for IVN. It's been more than 16 years ago that NXP was the first to develop and introduce the CAN standard to industry. Since then, NXP has been setting the standard in EMC performance. Until today, NXP has shipped more than 3 billion IVN devices to the industry. We know how to manage volume supply to more than 250 customers worldwide. Following our success story for CAN networks, NXP was the first to bring FlexRay on the road in 2007. Since then, NXP has shipped far more than 2 million innovative FlexRay devices to the market. At NXP, we never stop innovating. We have drastically reduced the power consumption of our products with the latest generations. The third generation of CAN transceivers consume as little as 10 microamperes in standby mode. The system basis chips as little as 57 microampere in sleep mode. NXP supports your efforts to shrink in size. We've introduced the HVSON package to the automotive industry in 2009, saving 70% board space compared to the standard SO packages. Our dual CAN saves another 20% space through high integration. We optimize the system cost by improving the integrated ESD protection to a level that makes external protection obsolete. We optimize functionality in our FlexRay transceivers for applications that don't need to further optimize your cost position. NXP saves our environment by removing hazardous substances like lead or halogens from our products.